Have you ever, like, really stopped to think about information? I mean, it's kind of a weird thing when you really think
It
about,
is, yeah, it's everywhere, right?
yeah, it's how we, experience the world, how we communicate. It's like in everything.
Yeah, from like tiny particles to huge weather
It
systems.
seems as fundamental as energy.
Right.
But here's the thing. We have all these super precise definitions for energy, but we kind of lack that universal definition for information, even though it feels just as important.
Yeah, it's almost a paradox. We all kind of know what information is intuitively, but when we try to define it scientifically, it gets really, really tricky.
Yeah, yeah. And that's why we're doing this deep dive today. We are going to try to explore a more formal scientific way to think about information.
Mm.
And we're going to use this really interesting research paper as our guide. It's called Architecture of Information
Mm.
by Yuri Parshin. And what's so cool about this paper is it looks at neural networks, the things that are powering a lot of AI, and it looks at them as energy systems.
Exactly. And for our listener, we know you're out there, you're curious, you want to learn these complicated things, and you want to learn them fast. Well, stick with us on this exploration. We're going to try and unpack some pretty dense ideas. We're going to make sure it's engaging and understandable, and hopefully you'll walk away with some really big aha moments about information.
Absolutely. This isn't a lecture or, a dry textbook.
Mhm.
Our goal is to kind of distill out the core insights from this paper and give you a shortcut to really understanding this perspective on information. Okay, so the paper kicks things off by touching on some existing ideas about information, like Shannon's information theory.
Yeah, it mentions Shannon's work, which defines information as basically a reduction of uncertainty. So the more information you get about something, the less uncertain you are about it.
Right, like imagine trying to guess what song is playing before they get to the chorus, right?
Okay.
With each lyric, you get more information, so
Yeah.
you're less uncertain.
Ex-
But the paper argues that while Shannon's theory is super useful for things like efficient data transmission, it doesn't actually tell us what information is fundamentally, just how it moves around.
Yeah, it's more about the practicalities, right? It's great for engineers who are building communication systems, but it doesn't quite explain the essence of information itself.
Right, okay. The paper also mentions Kolmogorov's algorithmic information theory, which is about complexity, yeah.
Yeah. Kolmogorov saw information as the complexity of something, which you could measure as the length of the shortest computer program needed to generate it. So a simple repetitive pattern would be low in complexity, low in information. And a completely random sequence would be high in complexity, high in information.
Okay, I get that. But the paper implies that this isn't the whole story either, right?
Yeah. While it gives us another way to kind of quantify information, it still doesn't fully explain how information interacts, how it's measured in different systems, whether those systems are physical or biological or even social.
So where do we go from there? The paper brings up quantum mechanics, which is where things always get really interesting.
This is where it gets really, really interesting. It looks at how people like von Neumann and Hawking thought about information within quantum mechanics. And here, information starts to be seen as almost like a property of a system's quantum state, related to how well you can describe it using measurable parameters. And Hawking, thinking about black holes, he took it a step further, suggesting that information is like a fundamental property of the system tied to its energy and matter.
So in the quantum world, information isn't just abstract, ones and zeros floating around. It's like intrinsically linked to the actual physical properties of things.
Exactly. The paper argues that quantum physics is like this bridge between thermodynamic entropy, which is about disorder, and informational entropy. Information becomes the structure of all the measurable things that define a system.
Okay, so how does that bridge actually work? This is where the paper gets into some formulas. And bear with us, listener. We're not going to get bogged down in math, but the connection here is important. So they compare Boltzmann and Shannon.
Yeah, so it highlights the similarities between Boltzmann's famous formula for thermodynamic entropy, which looks at the microscopic arrangements of a system, and Shannon's formula for informational entropy, which looks at the probabilities of different events.
Right. And on the surface, they seem to describe totally different things. One's about physics and heat, the other's about data and communication.
Right, but they look incredibly similar mathematically. And the paper points out that in thermodynamics, that idea of how many ways you can arrange a system at the microscopic level is basically a measure of probability. So it argues that this is analogous to the probability of events in Shannon's formula. It's just a different way of looking at possibilities and uncertainty.
Okay, I'm starting to see the connection. So the more ways a system can be, jumbled up at that microscopic level without us noticing any difference at the macroscopic level, the higher its thermodynamic entropy. And that's like having more uncertainty in an information system, right? More possibilities for what could happen.
You got it. And the paper even points out that if all of those microscopic arrangements are equally likely, then Shannon entropy becomes directly proportional to thermodynamic entropy. They're not completely separate ideas, just different perspectives on the same underlying principle.
That's a pretty mind-blowing concept, right? Information isn't just these abstract bits. It's tied to the number of possible arrangements of a physical system.
That's the direction the paper is heading. And
Ah,
to reinforce this link, it brings in Landauer's principle.
yes. The idea that erasing information has an energy cost, right?
Mhm.
You can't just delete a bit without generating a little bit of heat.
Exactly. Landauer's principle states that there's a minimum amount of energy needed to erase a bit of information, and it depends on the temperature of the system. So forgetting something, hitting delete, it's not free. When you erase information, you're decreasing the order of the system that's holding it, but you're increasing disorder in the environment by releasing that heat. So the total disorder of the universe still goes up, as it must, according to thermodynamics.
Okay, so we're building this picture of information as something closely connected to energy and entropy. But now the paper takes this really fascinating step where it reinterprets Shannon's formula in terms of actual, energy parameters within a system.
This is where the paper gets really insightful. It suggests that if we think of a bit not as a 0 or 1, but as a measurable value of energy, then the probability in Shannon's formula starts to reflect the relationships between these energy parameters.
So it's not just about how likely an event is to happen on its own, but how the energies within a system are kind of interconnected and influence each other.
Exactly. And the paper draws on how energy is structured in quantum physics and chemistry. These relationships themselves can be seen as a kind of energy called interaction energy. So it proposes that probability in Shannon's formula could actually reflect our, or a system's, lack of knowledge about the exact values of these interaction energies.
So instead of just abstract probabilities of isolated events, we're now talking about the concrete relationships between energies in a system.
Precisely. And the paper even provides a symbolic way to move from a sequence of probable events to a sequence of energy measurements. It introduces these gamma I terms, which represent the probability of a relationship between consecutive energy elements. You can almost think of them as an abstract version of interaction energy. And what's even cooler is that these gamma I terms can be linked to the weight coefficients in artificial neural networks.
That's a bridge I wasn't expecting. So those weights in AI, which we usually think of as just, numbers that connect things, they might actually have a deeper meaning related to energy interactions within the system.
That's what the paper suggests. But it's important to note that this connection is still somewhat abstract. It captures the statistical relationship, but not the full complexity of the energy interdependence itself. It's kind of like a weather map showing you patterns, but it's not the actual wind and temperature at every point.
Right. Okay. And it also highlights that the in-bit in Shannon's formula, the basic unit of information, that's not a direct energy measurement either, right? It's more like a generalized symbolic representation of an energy value, so it's still a step removed from the real physical energy.
Right. Whether you use binary or decimal or whatever system to represent it, the underlying energy is what matters, and the symbols can change. And this brings us to some key limitations of Shannon's formula when viewed through this energy lens.
What are they? What does the paper see as the main drawbacks of Shannon's approach in this context?
Well, firstly, those informational elements, they don't have any internal energy structure in Shannon's theory. They're just abstract symbols. Secondly, they're typically arranged in a linear sequence, which oversimplifies the complex web-like connections between energy elements in real systems. And thirdly, the connections between them are only treated statistically, not capturing the full interdependence of all the parts and the overall state of an energy-based system.
Okay, yeah, I can see how those simplifications might lead to problems, especially if we're thinking about things like creativity and AI. And the paper mentions this thing called the entropy gap in generative ANN, like those that generate text or images. What is that all about?
The entropy gap refers to this challenge where we want AI to generate things that have low informational entropy, meaning they're coherent, they make sense. But the way these models achieve that low entropy is by learning statistical patterns from their training data. And the problem is the most creative, novel outputs are often statistically rare. So these models, by focusing on what's most probable based on what they've seen, they tend to undervalue these potentially groundbreaking but rare connections. So they struggle with true novelty because they're too focused on what's statistically likely.
So it's like the AI is stuck in a rut, repeating what it's seen before, not really able to come up with something truly new and different.
Exactly, it becomes predictable. And the paper also warns about this danger of data inbreeding if we try to fix this by just training AI on its own generated data.
Right, like it's just going to keep recycling the same ideas over and over, getting less creative over time.
Exactly. It would be like photocopying a photocopy and expecting it to get better. You just lose detail and information. You end up amplifying the existing biases, and you eliminate any chance of introducing genuinely new information.
So the paper argues that to really solve this, we need a whole new way of thinking about information and how it relates to building intelligent systems.
That's the main argument. To get past these limitations and maybe achieve truly intelligent, creative AI, we need a paradigm shift, one that goes beyond statistics and dives deeper into the energetic nature of information and how it shapes the very structure of systems.
Okay, so the paper lays this groundwork, right? It examines these existing information theories and their limitations through this energy lens. And then it introduces this really powerful concept, the energy landscape. I've heard this in different fields, but what does it mean in this context, and how can it help us understand information better?
The energy landscape is this great metaphor, and the paper uses it to show how energy and information might actually be two sides of the same coin. It describes how any system, whether it's physical particles or information bits, or even biological cells or social groups, will naturally tend to move toward states of lower energy. It's like a ball rolling down a hill. It will settle in the lowest valley it finds.
So imagine like a topographical map, but instead of elevation, it represents the energy levels of different states a system could be in. The valleys are the low-energy, stable states, and the hills are high-energy and unstable.
Exactly. In physics, for example, if a ball is sitting on a table, that's a state of low potential energy. It's stable. If you push it up a ramp, you increase its potential energy, and it will naturally roll back down to a lower energy state. It's all about finding that minimum energy configuration.
Right, like in thermodynamics, systems always try to minimize their free energy. And these valleys in the landscape, they can be local or global, right? Like a little dip versus the absolute lowest point in the whole map.
Exactly. A system might get stuck in a local minimum, a relatively stable state, even if there's a much better global minimum out there. And this idea is important for understanding why some systems get stuck in suboptimal configurations.
So how does the paper describe the total energy of a system in this landscape framework? It brings up this concept of bonding energy, right?
It does. It presents a general equation for the total energy, which includes not just the energy of the individual components, but also the energy of the interactions between them. It's this interaction energy, often called bonding energy in chemistry, that really shapes the overall landscape.
And then there's this rest state energy landscape and a rest threshold. That sounds important.
Yeah, it's like the baseline energy of the system when it's not being driven by external forces. The rest state energy landscape describes the energy distribution within the system when there's no external energy flow, and it's at its maximum possible entropy. It's the most disordered it can be without changing its overall structure.
So it's kind of like the ground state energy of a system.
Exactly. The paper emphasizes that often reaching this minimal rest state energy involves simplifying the system's structure, minimizing the energy of its parts and connections.
Okay, and then it talks about bond energy and how that fits into the picture.
Yes. Bond energy, like the energy that holds atoms together in a molecule, actually reduces the total energy of the combined system. It creates what the paper calls wells and channels in the landscape, representing stable locations and pathways for energy to flow.
Okay, so how does this energy landscape concept apply to artificial neural networks? This is where things start to get really interesting, I think.
Yeah, this is where the paper makes some really important observations. So for most artificial neural networks, that rest state energy landscape seems to be static. It's fixed by those weight coefficients, the numbers that define the connections between neurons. And you might think of those weights as some kind of connection energy, but the paper argues that they're not really like the bonds in a molecule. They don't exist as independent energy elements.
So going back to that basic McCulloch-Pitts neuron model, those weights just kind of scale the input signals, right?
Exactly. They're more like multipliers than energy carriers. The paper suggests that maybe the sum of those weight coefficients going into a neuron could determine the depth of its potential while in the resting state, like how much energy it can hold or process.
It's like an analogy to the ionization energy of an atom. the energy needed to knock an electron loose.
Yeah, but the crucial point is that the formal neuron model in AI lacks that common energy foundation with real physical systems. It's still fundamentally an information model based on abstraction.
So in a way, those weights and ANNs represent this kind of conditional internal energy, but it's not truly structured or connected to the input energy in a real physical sense.
Exactly. The paper introduces this term pseudo-energy to describe those weight coefficients. It represents the error the learning algorithm is trying to minimize, not real physical energy.
And this pseudo-energy determines how the neuron responds to inputs, basically dictating what kind of input patterns will push it past its activation threshold.
Right. And the input energy in ANNs is typically normalized and constrained, which kind of mimics how our own sensory perceptions are limited. And because of these constraints and the learned weights, we get these specific patterns of activity microstates that lead to the overall output, the macrostate of the ANN.
And all of that together can be thought of as the system's free energy. So an ANN in the inference state, making predictions, is in a stable non-equilibrium, but its internal energy landscape, which is defined by those fixed weights, doesn't change.
Right. It's stuck in that configuration unless you retrain it. And then the paper introduces another important concept, the activation threshold, or TR2. It defines how much energy input is needed to trigger a change in a component, like a neuron firing.
So you have to provide enough energy to overcome that threshold before anything really happens.
Precisely. The paper has this analogy of water flowing on a surface with pits and channels, showing how energy might distribute itself within the landscape. And some areas will fill up, the low-energy wells, and then if enough energy flows in, it spills over into other areas, causing activation.
Okay, that's a good visual. And then there's that third threshold, TR3, for structural stability, which is about the strength of those connections within the system.
Yes. So if there's a huge influx of energy and no way to dissipate it, those connections between units can become unstable and break down. Imagine a bridge collapsing under too much weight.
Right, so too much energy without proper dissipation can destabilize the whole structure. And it's interesting that the paper points out that those activation functions in ANNs, which determine when a neuron fires, they don't fully capture that energetic aspect of exceeding a real physical threshold.
Right. And these three thresholds, TR1 for the rest state, TR2 for activation, and TR3 for structural stability, they all determine how resilient the system is to changes. Multiple failures at that TR3 level, those connections breaking, that can lead to a big system-wide shift, a bifurcation point.
Okay, so this way of looking at energy landscapes and thresholds, it leads the paper to propose a new way to classify systems, right? Adaptive, evolutionary, and self-organizing. How are those different in this energy-based view?
Exactly. It suggests we can categorize systems based on how their energy landscapes can change over time. Adaptive systems can modify their thresholds or energy parameters in response to the environment. Evolutionary systems actually restructure their fundamental energy landscape over longer periods, maybe adding or removing components. And self-organizing systems are the most radical. They can create entirely new energy landscapes and structures based on the energy flows within them.
And the key to all of that, according to the paper, is understanding the system's energy structure.
Right. It's not just about tweaking parameters, it's about understanding how energy shapes and reshapes the very foundation of the system.
And this could be revolutionary for both systems theory and AI. If we could actually harness those mechanisms of energy transformation, it could lead to AI that can truly learn and adapt in much more sophisticated ways.
That's the potential, yeah. Moving beyond just tweaking those statistical weights and tapping into these deeper energetic principles.
Okay, so after building up this framework of energy landscapes, the paper shifts gears and looks at a specific type of neural network, the Hopfield model. This is an older model, right? But it was one of the first to try and connect information theory and physics.
Yeah, the Hopfield model was developed back in the 1980s, and it was a really influential early attempt to bridge that gap between information processing and physical principles using the idea of energy landscapes. It tried to make these direct comparisons between the states of its neurons and the energy states of a physical system.
And it even borrowed a concept directly from physics as its prototype, the Ising model for ferromagnetic materials.
Right. The Ising model describes how those tiny magnetic moments or spins in a material can align to create a larger magnetic field. It's all about how local interactions between these atomic magnets can lead to global order in the material. This order depends on temperature and the strength of the interactions, which are represented by an interaction energy term.
So the Ising model is basically saying that at lower temperatures, the system wants to be in a state where all the spins are aligned, because that's a low-energy configuration.
Exactly. And how those spins flip from one orientation to another, that happens randomly, influenced by the temperature of the system. There's this thing called the Boltzmann distribution, which describes the probabilities of different energy states. At higher temperatures, you get more random flipping. At lower temperatures, they tend to stay aligned. Now, the Hopfield model takes some of these ideas about energy states and minimization, but it adapts them to create an associative memory, a network that can retrieve stored patterns.
And the key difference the paper highlights is that in the Ising model, those spin flips are random, driven by temperature. But in Hopfield, the state changes of the neurons are deterministic, based on the correlations they've learned.
Exactly. In Hopfield, each neuron updates its state based on the weighted sum of its inputs from other neurons. Those weights represent learned correlations, and it's all aimed at converging to a specific memory pattern. The Hopfield model also has its own energy function, mathematically similar to the Ising model.
But the paper points out that unlike in Ising, where the probability of a spin flip depends on the temperature, the Hopfield model uses a fixed threshold for neuron state changes. It doesn't have that dynamic, temperature-dependent aspect of a real thermodynamic system.
Right, it's more of a simplification and abstraction. So the Hopfield network ends up being more an informational system, even though it uses this language of energy landscapes and energy functions.
And while Hopfield refers to the energy landscape as the set of all possible neuron states, the paper argues that it doesn't truly define an equilibrium resting state in a real physical sense.
You got it. But here's the interesting thing. The paper then shows that, according to the Hopfield energy function itself, that resting state energy landscape can be seen as being shaped by the sum of all those weight coefficients connected to the inputs of each neuron. And those weights are learned during training using this rule called Hebbian learning, which strengthens connections between neurons that are active together.
So the Hopfield network has this theoretical minimum energy state. But in practice, it tends to settle into these individual minima that correspond to the specific patterns it has learned to remember.
Exactly. And the way each neuron decides to change its state based on the input from other neurons, it's kind of like a correlational vote. Each connected neuron gets to vote on whether the current neuron should be active, and the weight of that vote is determined by the strength of the connection.
So it's not so much about being pulled towards an energy minimum. It's more like a collective decision-making process based on those learned correlations.
That's a better way to put it, yeah.
Okay, so the paper concludes that even though Hopfield uses this language of energy and landscapes, it's more of a pseudo-energy system. But the concept itself is still valuable, right? Reaching the minimum of the Hopfield energy function means the network has found a stable state and reduced its informational entropy related to those stored patterns.
Precisely. But the paper also points out that the common idea of attractors in Hopfield, it's a bit misleading. There's not really an energy state that's actively attracting the network. It's more about that correlational voting process leading to a stable pattern.
And it also draws this comparison to the Ising model. If the Hopfield energy function indicates a decrease in energy and information entropy, the paper suggests that the analogous function in the Ising model might actually imply the production of both thermodynamic and information entropy in more complex systems, which is kind of aligning with those ideas from quantum information theory and those dissipative systems we talked about earlier.
It is. It's a fascinating connection between these two seemingly different models.
So maybe a simpler way to understand Hopfield is just to focus on its initial state and those learned correlations, with the energy function being more of a mathematical tool to demonstrate its tendency to stabilize.
Yeah, that's a good way to think about it. And the paper offers an alternative way to think about the Hopfield network energetically. It says that the internal energy is just the energy of its individual neurons, the connection energy isn't really defined, and the changes in neuron states are driven by external input energy exceeding certain thresholds determined by those weight coefficients.
So in that view, the Hopfield energy landscape is shaped by the specific patterns it has learned from the outside world.
Right, it's an internal model of its experience, so to speak.
And the energy function represents how that external input energy gets redistributed within the network, with each neuron's threshold acting like a gatekeeper.
Exactly. And the overall decrease in energy within the network actually aligns with the idea of increasing entropy in the outside world. It's all about energy dissipation.
But the paper also points out a problem with the Hopfield model. It doesn't have a clear stopping mechanism. It just keeps updating based on the rules, so you need something external to tell it when to stop.
Right.
So to sum up, The paper classifies the Hopfield network as a system with a fixed structure, a static resting state energy landscape that's formed quickly during learning, and then a dynamic energy landscape during the retrieval process when it's minimizing information entropy.
Exactly. And it's that fixed structure and the lack of true connection energy that limit its capabilities compared to more dynamic systems.
Okay, so now the paper zooms in even further. It looks at the energy model of a single individual formal neuron, the McCulloch-Pitts model, or MCP. This is like the most basic building block of artificial neural networks, right?
It is. The paper wants to model this simplified informational unit as an energy system so we can really understand its limitations compared to a real biological neuron.
And they start with the classic binary MCP neuron, where the weights are either -1 or +1, and it has a simple on-off activation function.
Yeah, it's the most basic version. And the paper explains that in its resting state, the MCP's energy landscape is mostly determined by those weight coefficients, which dictate how much input energy is needed to make the neuron fire.
And it's important to remember that this is just a single isolated unit. We're not considering the complex energy interactions that happen in a real brain or even in more sophisticated artificial networks.
Right, this is like the bare minimum. And the paper includes this diagram, Figure 2, which shows the energy model for this single MCP neuron. It shows input energy, output energy, that internal energy calculated from the weighted inputs, and even introduces this idea of Maxwell's daemon to represent the learning algorithm.
So the internal energy of this MCP neuron is basically split into two parts based on the weights. There's excitatory energy from the positive weights and inhibitory potential from the negative weights.
Yeah, and that inhibitory potential, the sum of those negative weighted inputs, that determines how much input energy is needed to make the neuron fire. It's visualized in Figure 3 as the depth of the potential energy well.
So the deeper the well, the harder it is to make the neuron fire.
Exactly. And then the output energy of the neuron, that's usually normalized. And the paper connects this normalization to Landauer's principle, suggesting that even generating that output has an energy cost associated with it.
And this Maxwell's daemon, we've heard that before, it represents the learning algorithm, right?
It does. It's this external agent, like backpropagation in a larger network, that adjusts those weights during training. And it does that by supplying pseudo-energy to nudge the weights in the right direction to reduce the error in the neuron's output.
So the paper defines the microstates of this neuron as those specific combinations of weighted inputs that lead to a particular output, which can be either active or inactive.
Exactly. And it then links the probability of the neuron being active to its thermodynamic entropy, specifically the number of different microstates, those input combinations, that can lead to the neuron firing.
So a deeper well caused by stronger inhibition would mean fewer input combinations can overcome the threshold, right?
Exactly. And that means a lower thermodynamic entropy for the active state. And the learning process, by adjusting the weights, it's essentially restricting the possible input combinations that lead to activation.
So the learning process is kind of shaping the energy landscape of that individual neuron, making it more selective.
Precisely. And then the paper brings back Shannon's informational entropy and shows that it also decreases as the probability of the neuron being active moves away from 50%, either becoming very likely or very unlikely. And this corresponds to that decrease in thermodynamic entropy we just talked about.
Right. So the learning process is doing the same thing to both types of entropy, thermodynamic and informational.
Exactly. The paper then makes this interesting connection to Gibbs free energy.
Ah, yes, the energy available to do useful work. How does that apply to a single neuron?
Well, it's not a typical interpretation, but the paper argues that if you think of the output of a neuron as its ability to perform work by contributing to a larger internal model, then the analogy to Gibbs free energy kind of makes sense.
Okay, so the structured part of the neuron's output, the part that actually helps the network learn, that's like the Gibbs free energy, and the unstructured part would be like wasted energy, increasing the system's entropy.
Right. In the MCP model, this formation of structured output, that primarily happens when the neuron is in the active state. The inactive state is more like a loss or a lack of useful work.
And the paper shows that after learning, the structured output energy reaches a maximum, and this corresponds to minimum entropy for the learned patterns.
Yes, which is similar to those dissipative systems we talked about before. They create order locally by increasing disorder elsewhere.
Okay, so the big takeaway from this single neuron model is that information is abstract, linked to energy only indirectly. The internal energy is basically pseudo-energy from the learning algorithm, and it doesn't have the same rich structure as real physical energy. But during learning, This structured output energy does emerge with minimal entropy, suggesting it's forming an internal model of what it's learned.
Exactly. So we've got this foundation now, and we can use it to analyze more complex, multi-layered networks.
Okay, so how does this energy-based view work for networks with multiple layers?
Hmm.
The paper uses that image of potential wells and the hidden layers, right?
Yeah. Figure 4 shows the energy landscape of a multi-layer perceptron, MLP, as a series of potential wells with different depths. Those wells represent the individual neurons, and their depth reflects the strength of the features they've learned.
But even in these multi-layer networks, there's still no real energy connection between units, right?
Right. The weights determine the depth of the wells, but they don't represent actual energy flowing between neurons. So the system needs to amplify the signal as information passes through, which isn't very efficient.
Yeah, that's a big difference from biological systems. And the formation of those neuron energies is still driven by minimizing that pseudo-energy through the learning algorithm.
It is, and the paper suggests that because these multi-layer networks are essentially just collections of those MCP-like units, their overall entropy behaves similarly to what we saw in that single neuron model.
And it brings up the information bottleneck theory, which has shown that information entropy decreases in the hidden layers during training.
Right. And that decrease in entropy comes with a decrease in the variability of neuron responses, meaning there are fewer possible microstates, and that's a reduction in thermodynamic entropy. It's like that single neuron behavior, but on a larger scale.
So the learning process is essentially compressing and filtering the information as it goes through those layers.
Exactly. And it's all being driven by this minimization of pseudo-energy.
And the paper calls these kinds of ANNs first-type networks, which include CNNs that work with segmented input like images. It classifies them as energy systems with a fixed structure, a static resting state energy landscape shaped by the learning algorithm, and deterministic energy dynamics as the system minimizes entropy.
Right. And it highlights that this fixed structure and the reliance on those individual neuron energies, they limit the accuracy of these models, especially as the number of things they need to learn increases.
Okay, so now for something different. The paper contrasts these first-type networks with text-generative ANNs, like GPT. How are those different from an energy perspective?
Generative models, or what the paper calls second-type networks, have a very different energy landscape. Instead of individual neuron energies, the dominant factor is the connection energy, represented by the weight matrices that link the different parts of the network.
So those weights aren't about individual neurons anymore. They're about the relationships between words and concepts.
Exactly. The individual units, those tokens representing words or the embeddings, they're more like static elements in this landscape. And those weight matrices determine the strength of the connections, the depth of the potential channels between those elements.
So it's like the weights are forming the pathways for information flow, rather than defining the energy of individual units.
Precisely. And the neurons in these generative models are learning to make connections between those elements. They're figuring out which words tend to go together, what kind of grammatical structures are common.
And the paper shows a simplified version of this energy landscape in Figure 5, highlighting that sequential flow and divergence of energy.
Right. So it's a very different picture than those first-type networks. It's all about the connections.
And because there are so many weights and layers in these models, the space of possible microstates is absolutely massive. And during inference, when these models generate text, they have to somehow navigate that huge space to find a good output.
Right. They do that by reducing the possibilities, selecting the most probable token connections based on what they've learned. And this is actually the opposite of what happens in those first-type models where the microstate space gets reduced during training.
So in a way, these generative